Good evening, viewers. So, welcome to another edition of NAMSSN tutorial. So, today we are going to discuss calculus of residue. Um, course back, course. It should be complex analysis. Good evening, viewers. So, welcome to another edition of NAMSSN tutorial. So, this is a complex analysis one, and today we are going to discuss about calculus of residue. Before we talk about residue and its application, so there are some things that we need. So the first thing is what is a contour? So a contour is a curve or path. A contour is a curve that provide a precise that provide that provide a precise definition of the curve in a complex plane. Now, what do we mean by contour? In the beginning of this course, if I have something like z plus 1, let's say is equals to 2, it means that z is a circle. If I have z plus 1 equals to 2, it means this z is a circle. Z is a circle centered at, if z plus 1 is equals to 0, z equals to minus 1. So centered at minus 1. And this 2 is radius 2. So if I want to sketch it, I'm going to have y and x centered at minus 1. It means that minus 1 will be the center of that circle. X equals to minus 1. From here, this side will be the center. Radius 2. The radius of the circle will be 2. From here to here is 1. From here to here now, 1. So my radius will be like this. And then if I have radius 2 here now, I'm going to have a minus 3. Here, this is how the curve will be. This is 1. So this curve is what we call a contour, a path that describe a function in a complex plane. So this means that z is a curve centered at minus 1. That is, minus 1 will be the center. The radius will be 2. That is, from here to here is 2. From here to here is also 2. So that is a contour. So if I also have something like absolute value of z equals to 1, this is like no, this one doesn't have anything here. It's like having z plus 0 equals to 1. It means z is a circle centered at 0, radius 1 unit. So if I want to sketch the contour, it will be like y, x, 0, which is the origin, will be our center. Then radius will be 1. From here to here is 1. From here to here is minus 1. Then we are going to have a path like this. So that is a contour z, absolute value of z equals to 1. If I also have absolute value of z, let's say plus 3 over 2 equals to, let's say, 2, for example. It means z is a circle centered at where? If z plus 3 over 2 equals to 0, it means minus 3 over 2 will be the center. centered at -3/2, radius 2. That is, we are going to have origin. The center will be 3 - 3/2. -3/2 is like 1.5, -1.5. Let's say I put that -1.5 here. And the radius is 2. If I add 2 to the right, -1.5 from here to here, let's say this is 1. This is 1. This is 0. This will be 0.5. So from -1.5 to 0.5 will be 2 now. -1.5 to 1, that's like 0.5. 1 to 0, that's 1, 1.5. Then 0 to 0.5, that's 2. So what will be the length of this edge? -1.5 plus 2, -3.5. That is how the curve will be. That is a contour. Now the next thing is we also learned about analytic function. A function is analytic if it is differentiable at a point z0 and is also differentiable at the neighborhood of that z0. So now let's talk about singular point or pole of a function z. Now the definition is the singular point, let's say z equals to a, is a point where that function z is not analytic. So where a function stops being analytic is the singular point or the pole of that function. So how do we know that, hey, this function will not be analytic? If you remember from our complex variables, how do we test for analytic? We take the partial derivative. I say f of z equals to 1/z. I will express it in terms of u plus iv. Then I will take the partial derivative of the Cauchy-Riemann equation. Now, this function will not be analytic if this z is equals to 0. That is, this fraction will be undefined. No, if I have something like 1/z plus 3, this fraction will be undefined if z is what? If z is equals to -3. So that -3 is the singular point. So for example now, let's say f of z equals to 1/z minus 2. So what is the pole of this function, or where is the singular point? So we just say the pole is this z minus 2 when is equals to 0. So if z minus 2 equals to 0, z equals to 2. So it means that 2 is the pole of this function z. That is, this function will not be analytic at z equals to 2. Another one. So what is the pole of f of z equals to 1/z square minus 3z plus 2? 1/z square minus 3z plus 2. So this function will not be analytic when the denominator, so the pole will be at where this z square minus 3z plus 2 when is equals to 0. And if this z square minus 3z plus 2 equals to 0, so solving this, we are having a z minus 2, z minus 1 equals to 0. So z equals to 1 or 2. So 1 or 2 are the pole of that function. Okay. Okay. So let's discuss the pole of f of z equals to 1/sin z. So look at this one. F of z equals to 1/sin z. Where are the pole of this function? As I said earlier, that the pole is when this fraction, the denominator, sin z is equals to 0. And if sin z is equals to 0, z will be what? Sine inverse of z. Sine inverse of 0. Sine inverse of 0 is equals to what? 0. But instead of using 0, it will be n pi, you know now. Or sin n pi, if n is 1, sin pi is 0. Sin 2 pi is 0. Sin 3 pi is 0. And not like that. So where n are 1, 2, 3, and not like that. So we can say that z1, it is 1 pi. Z2 is 2 pi. Z3 is 3 pi. and so on. So it means that pi, if I put pi here, 1 over sine pi, to give me undefined fraction. If I put 2 pi here, 1 over sine 2 pi, to give me an undefined fraction. So the pole of this f of z equals to 1 over sine z is pi, 2 pi, and all like that. So now, if I want to find the pole of f of z equals to 1 over z minus 2 all squared, for example, z minus 2 all squared. So the pole of this z minus 2 all squared, so the pole will be at where z minus 2 all squared equals to 0. If I'm having this, z minus 2 all squared equals to 0, obviously z will be equals to what? It will be 2, because if I take the square of both sides. But how many 2 am I getting? This is z minus 2 all squared. So this is z equals to 2 twice, right? If you solve this, you get 2 in 2 places, like z minus 2, z minus 2. So in a case whereby I'm having a value, like the value is occurring twice or 3 times. So if it is twice, we call it pole of second order. Z minus 2, pole of second order, because z equals to 2 in 2 places. So if it is z minus 2 raised to power 3 now, you know, our answer will be z equals to 2 3 times. So that will be pole of third order. Pole of third order. Okay. So what is the pole? So find the pole of f of z equals to 1 over z square minus 1 z plus 3 raised to power 4. So the pole of this one will be, the pole will be at where the denominator is equals to 0, z square minus 1 and z plus 3 all raised to power 4 when is equals to 0. So if z square minus 1 equals to 0, so we can factorize this into z minus 1, z plus 1, z plus 3 all raised to power 4 equals to 0. So the first one will be equals to 0. If z minus 1 equals 0, z equals to 1. This is one pole. If z plus 1 equals to 0, z equals to minus 1. This is another single pole. Call this one single or simple pole. And the other one here, if z plus 3 raised to power 4 equals to 0, it means that z will be what? Minus 3. In how many places? 4 times. 4 times. So this will be what? Pole of what? Pole of fourth order. So this is a pole of fourth order. Pole of fourth order. Pole of fourth order. So that's the basic way of understanding what is contour and what is pole, and how do we sketch contour on x and y plane. Now the next thing is residue. Residue, how do we find the residue of the function? So we have about 4 rules that guide finding residue of any function z. So number 1 is residue at simple pole. Residue at simple pole. So residue at simple pole is a limit of z approaches a of z minus a times that function z. That does it. So residue at simple pole is a limit as z approaches a, where a is that pole. Let me put it where a is the what? Is the pole. Where a is the pole. So limit as z approaches a, z minus a times f of z. So for example, let's find the residue. Let's find the residue at the pole of this function of f of z equals to 1 over z square minus 3z plus 2. F of z equals to 1 over z square minus 3z plus 2. Now, what are the pole of this function? The pole will be at where? The pole will be z square minus 3z plus 2 equals to 0. If z square minus 3z plus 2 equals 0, factorize and solve. This is z minus 2, z minus 1 equals to 0. Z equals to 2 or 1 are the poles. Now we now want to find the residue at each pole. We have one is 2, the other one is 1. So residue at this 2 now, I'll say res 2. Residue at z equals to 2. Go by this formula. That will be limit as z approaches that 2 of z minus a. Here our a is 2. Z minus 2 times f of z. This is our f of z. 1 over, instead of putting z square minus 3z, I will just change it to z minus 2, z minus 1, or z minus a f of z. Here our a, the first one I'm considering is 2. Limit as z approaches 2 of z minus a, z minus 2, f of z. This is f of z. So z minus 2 will cancel z minus 2. So we are now taking the limit as z approaches 2 of 1 over z minus 1. So if z equals to 2 here, put 2 here, that's 1 over 2 minus 1. That is 1. So the limit is 1. Then residue at the other pole, residue of 1, that will be limit at z approaches 1 now, times z minus a. Here our a is 1. Z minus 1, f of z, 1 over z minus 2, z minus 1. So z minus 1 will cancel z minus 1. We are going to have 1 over z minus 2. So if I put 1, that will be minus 1. So 1 over z minus 2 will be minus 1. So the other one, that will be limit z approaches 1, 1 over z minus 2. If you put 1 here, that is 1 over 1 minus 2. That is minus 1. That is how to find the residue at simple pole. So find the residue of 1 over z squared plus 1 at its pole. Yeah, 1 over z squared plus 1. So what are the pole of this one? The pole will be at where? When z squared plus 1 equals to 0. And we can actually factorize this into what? Z plus I, z minus I, difference of 2 square. So if z plus I, z minus I equals to 0, that's z equals to I or minus I. So the residue at z equals to I, res I, let's say res I, it will be what? Limit at z approaches that I of z minus that I, that's z minus I, times f of z. These are f of z. But instead of putting this, I'll say 1 over z plus I, z minus I. So z minus I will cancel z minus I. We are putting the limit as z approaches I. That's 1 over I plus I. 1 over 2I. Then the residue at z equals to the other pole, minus I. That will be limit as z approaches that minus I. Z minus this stuff. That will be z minus minus I. This one will be z plus I times f of z. 1 over z plus I, z minus I. So what will happen? Z plus I will cancel z plus I. Then we are having 1 over z minus I, where our z will be minus 1. That will be 1 over minus I minus I. 1 over minus 2I. That is our residue at simple pole. Just equate to 0 and then take the limits one after the other. So residue at each pole. Now, another case of residue is residue at n poles. That is when we have a pole of second order, pole of third order, pole of whatever order. So if I want to find residue at nth pole, it will be limit as z approaches that a, where a is our pole, 1 over n minus 1 factorial dn minus 1 dzn minus 1 of z minus a times f of z. So it looks somehow scary, but it's yeah. So residue at n pole, it will be limit as z approaches a of 1 over n minus 1 factorial dn minus 1. The meaning of this dn minus 1 is that n, oh yeah, it's true. So z minus a raised power n f of z. So the meaning of this dn minus 1 is that if you are dealing with pole of second order, you differentiate once. If you are dealing with pole of third order, you differentiate twice. So let's check example. So let's obtain the residue. Obtain the residue of f of z equals to z plus 3 over z minus 2 squared and z plus 1 at its pole. So what are the pole of this one now? Pole will be at where? Pole will be at when z minus 2 all squared z plus 1 equals to 0. If this z minus 2 all squared equals to 0, or z equals to, this one is z equals to minus 1. So this will be, z will be what? 2, twice, Abi. So this is z equals to 2 twice. This is pole of what? Second order. Because z will be, z is 2 in 2 places. Or z equals to minus 1. So if I start from here, these are simple pole. This is a pole of second order. So if I first take the residue of minus 1, residue of minus 1, that's residue of simple pole, that will be limit as z approaches minus 1, that z minus 1, that will be z plus 1 multiplying f of z. Here is our f of z. They've already factorized it. So z plus 3 divided by z minus 2 squared z plus 1. So z plus 1 cancels z plus 1. Put minus 1 into whatever we are having left. So minus 1 plus 3, that's 2. Put minus 1 here. Minus 1 minus 2, that's minus 3. Minus 3 squared, 9. So the pole of this one, the residue of this one is 2 over 9. Then the residue at z equals to 2. This one is a double pole. It means our n is 2. Our n is 2. So that will be 1 over 2 minus 1 factorial. The what? The 2 minus 1. That's the first derivative. Because if I put 2 here, 2 minus 1, that will be d1 divided by the z1 of z minus a. Here our a is 2. Z minus 2 raised to power, here n is 2 times f of z. Z plus 3 divided by z minus 2 square and z plus 1. So z minus 2 square will take care of z minus 2 square. So the residue will be 2 minus 1, 1 over 1 factorial, that's 1. Well, that one is not significant. D dz. What are we now differentiating? We are differentiating z plus 3 divided by z plus 1. Don't forget the limit. So limit at z approaches 2. So how do I differentiate this? Quotient rule. So quotient is we are going to have over v square z plus 1 all squared, write z plus 1, differentiate z plus 3, that's 1. V du minus, write z plus 3, differentiate z plus 1, that's 1. So in that case, this will be, don't forget we are taking the limit as z approaches 2. So this will be z plus 1 minus z. Z and minus z will go. 1 minus 3 minus 2 over z plus 1 all square at z equals to 2. So if your z is 2 here, that's 2 plus 1, 3. 3 square, 9. That will give us minus 2 over 9. That is the residue at that pole. Whenever we are dealing with 2 or 3 or whatever, so just take the derivative like this. So the next case of residue is a residue of coefficient. Residue of coefficient of 1 over z in Laurent series. Now, so let's find the residue of e raised to power z divided by z raised to power 6, for example. So now this one, the pole is 0. If I have z raised to power 6, z raised to power 6 equals to 0, z equals to 0 in 6 places. So, but there's another way of finding the residue instead of differentiating 5 times. So we just go and borrow from our idea of expansion that we did in our previous video. So this one will be like 1 over z raised to power 6. We know that e raised to power z is a known series. So if I expand e raised to power z, e raised to power z is 1 plus z square plus z cube plus z square over 2 factorial, z cube over 3 factorial, z4 over 4 factorial, z5 divided by 5 factorial, and so on. So if I now multiply both sides by over z6, that's a 1 over z6, z over z6, that's 1 over z5. Z square over z6, that's 1 over 2 factorial and z4. Z cube over z6, this will be 1 over 3 factorial z3, because this one will remove 3. Plus z raised to power 4 over z6, that's 1 over 4 factorial z square. Z5 over z6, that's 1 over 5 factorial z, and so on like that. So we now take the coefficient of 1 over z. Where is 1 over z? 1 over z. Yeah, this place. So what is the coefficient? So coefficient of 1 over z is what? 1 over 5 factorial. That's 1 over 120. So our residue of this one is 1 over 120. 1 over 120. So another one of this kind. Let's find the residue of sine z divided by z square. Sine z divided by z square. Okay, I can take the expansion of sine z. I already know that sine z is an oscillating function. I'm going to have 1 over z square. Sine z is z minus z cube over 3 factorial plus z raised to power 5 over 5 factorial minus z raised to power 7 over 7 factorial, and so on like that. So if I now I think I need like 2 or 3 more so that I'll get the desired. So the next one will be plus z raised to power 9 over 9 factorial. The next one will be minus z raised to power 11 over 11 factorial. So let me stop there. So multiply both sides by over z square. Oh, it's already here in first expansion. So this is 1 over z minus z over 3 factorial plus z square divided by 5. Yeah, z square divided by 5 factorial minus z5 divided by 7 factorial. So I don't need more expansion again. So I've already gotten 1 over z. What is the coefficient of 1 over z? That's 1. So the residue of this one is equals to 1. Just take the expansion and then expand and divide by whatever we are doing. If you see something like this, so if I want to find the residue of 1 minus cos z over z, just take the expansion of cos z, divide by z. The one that gives us 1 over z, the coefficient, is our residue. Okay, so viewers, I will leave that one for you to attempt. Then the last part of residue is residue of f of z is equals to a function of z like this divided by phi of z like this. Now look, where phi of a is equals to 0, phi prime of a equals to 0. Residue of this stuff, residue of f of z equals to a numerator divided by another denominator, where the pole, if I differentiate it and I put the pole, I get 0. How do I find the residue of this one? So the residue, sorry, where phi of a is 0, not phi of pole, phi of a is 0. So the residue will just be the derivative of this stuff, of this denominator at z equals to a. That's the residue. So the derivative of that's phi of a divided by rho prime of a. That's the residue. So the condition is that this one will give me 0 if I put a. That is, if I substitute my pole, I'll get 0. So if I now want to find the residue of something like this, it will be phi of a, that is where a is the pole, and then divided by the derivative of this one at z equals to a. So for example, let's find the residue. Find the residue of f of z equals to tan z. F of z is equals to tan z. You know, if I want to turn this one to a rational function, I will say f of z will be sin z divided by cos z. Now, what are the pole of this sin z over cos z? Pole will be at where? Pole is when we equate the denominator to 0. So pole is when cos z is equal to 0. And if cos z equals to 0, z is a cos inverse of 0. Cos inverse of 0 is what? Cos 90 degree, that's 0. So I'll say that will be n pi over 2. I generalize that, n pi over 2. So z equals to n pi over 2. So when n is 1, I'll say my pole will be at pi over 2. When n is 2, it will be pi. When n is 3, it will be 3 pi over 2. So these are my pole. So I will now do what? I will now put one of the pole here now. Let's say pi over 2 now. I'll put pi over 2. That is the numerator. You put that pole a, then you differentiate the denominator. So my residue at one of the pole, let's say at pi over 2, it will be sine pi over 2 divided by the derivative of this denominator at pi over 2. So if I differentiate cos z, I'll get sine z, right? At pi over 2, that will be sine pi over 2. What we are saying is that if you're having a function like this, take the pole. After finding the pole, here we have multiple pole, pi over 2, pi 3, pi over 2, and so on like that. So if I want to be specific, at this pole, pi over 2, so the residue at this pi over 2 will be, put that pi over 2 on numerator, and then differentiate the denominator, put pi over 2 again. So if I put pi over 2, I will have sine pi over 2. If I differentiate cos z, so that will be minus sine z. So minus sine z at z equals to pi over 2. And I know that sine pi over 2, sine 90 is 1. Sine pi over 2 is also 1. With this minus, that's minus 1. I'm going to have minus 1. So the residue of this stuff is z equals to, the residue at pi over 2 is minus 1. Now, all the things we've learned now, where are we applying it? So we want to apply it to solve integration specifically. So the first thing is how to sketch, contour, how to find pole, and how to find residue. So where we are going now is residue theorem. So we basically use residue theorem to solve definite integral in real and in complex. Now, residue theorem. So this is where work is now. So residue theorem states that if f of z is analytic, if f of z is analytic, comma, in a closed curve C, in a closed, that is in a contour, That's what they mean by that. In a closed curve C, except a finite, except at a finite number of pole, at a finite number of pole. So you already know what pole is within that curve, within C, comma, then integral of f of z dz is equals to 2 pi I times sum of residue. R is my residue. What this theorem is talking about is that if I'm having a contour like this, and then inside that contour we have some pole. Let's say this is one pole, this is another pole, we have another one. So the integral of this function z, you observe that, let's say this is a pole A1, pole A2, pole A3. You observe that it's only pole A1 and A2 that are within that curve. It's only A1 and A2 that are within that curve. A3 is outside. Then the integral of this function will be residue at this A1, residue at this A2. We add them together, we multiply it by 2 pi I, where 2 pi I is just like moving around a circle. Again, in a closed curve now. Inside that closed curve, we now have some finite pole. Finite is the pole that is countable. Let's say we're having pole A1, A2, in fact, let's say A4. And then you observe that within that curve, within this contour now, is only A1 and A2 that are within it. Now, he said that if a function is analytic in a closed curve, except at a finite, so the one that's the number of poles that are outside the contour are A3 and A4. So A3 and A4, they lie outside the contour. Then the integral of this function will be the residue of this simple pole. The residue of this simple pole, we add them together. That is summation R. Whatever we get, we multiply it by 2 pi I. That's basically what residue theorem is all about. So let's solve one example. So the first example here. So we want to evaluate using residue theorem. Want to evaluate integral of C of 1 plus Z divided by Z and 2 plus Z dz. Where C is what? Where C is a circle such that absolute value of Z equals to 1. Where C is a circle such that absolute value of Z equals to 1. Now the meaning of this C, it means that we are integrating around the circle. Don't forget from our line integral. So if I'm moving like this, moving like this, moving like this, so that one is line. So C now, we are moving around the circle. So C, if you can see it like this, sometimes they can put it in this form. They put integral and then they put a small circle inside it like this. It means you are moving around the complete circle. This is where we are going to start from. What is the meaning of this Z plus Z equals to 1? The first thing that I mentioned is that this Z equals to 1 is a circle at center 0, radius 1. You first sketch the contour. So the meaning of absolute value of Z equals to 1, it means a circle. This is like Z plus 0, right? Centered at where? Centered at 0. Radius is equals to 1. It means this is 1. If radius is 1, this side will also be minus 1. Then you sketch the contour. That was our C. This is the part. Y and what? And X. After getting the contour, you see this function you are integrating is your f of z. From here, we say our f of z equals to 1 plus z divided by z and 2 plus z. Please don't mind my 2 and z. This is 2, this is z. Now the next thing is to do what? We obtain the pole. How do we find pole? Pole is when we equate the denominator to 0. So the pole will be at z bracket 2 plus z when they are equals to 0. If z and 2 plus z equals 0, it means that z equals to 0 or 2 plus z equals 0. That's minus 2. It means that is 0 and minus 2. They are the pole. Then you now go back to the contour. You put 0. Where is z equals to 0? This is z equals 0. This is one pole. Where is z equals to minus 2? Minus 2 will be around this part. So what do you observe? You observe that it's only this z equals to 0 that are within this curve C. Z equals to minus 2 is outside. So to find this integral, to evaluate this integral now, we now take the residue at this Z equals to 0 alone. We ignore this because the theorem says that except at a finite region, that other region that are outside the pole, we ignore that one. So we now take the residue. This is a simple pole, simple pole. We take the residue at Z equals to 0, residue of this one alone. We leave this. Suppose that this Z equals to 2 is also within the contour. We also take the residue at that point too. So, but here now, that minus 2 is outside. So if I take the residue at Z equals to 0, it will be, don't forget, limit as Z approaches 0 of Z minus 0 times f of Z. This is our f of Z. F of Z is a 1 plus Z divided by Z 2 plus Z. Okay? Z minus 0 is Z. So this one will cancel. So we are now taking the limit as Z approaches 0 of 1 plus Z over 2 plus Z. Don't forget Z is 0. If you put 0 here, put 0 here, our residue will be 1 over 2. Our residue will be 1 over 2. Then the solution of this integral now. So the integral of C 1 plus Z divided by Z 2 plus Z dz is equals to what? 2 pi I multiplied by the residue. That will be 2 pi I times, what is our residue? Our residue is 1 over 2. 2 cancel 2. What's our answer? I pi or pi I. So the solution of this is I pi. It's just 3 steps. So the first step is that sketch this contour. That contour will shape how our solution will be. Sketch the contour, find the pole. Then go back to contour. Z equals to 0. Is it within the contour? Yes. Z equals to minus 2 is outside. So we ignore the one that is outside. The one that is within the contour, we find the residue at that point. That's simple pole. So this is the residue at Z equals to 0, 1 over 2. Then the integral will be 2 pi I times 1 over 2. Example 2 on residue theorem. So let's evaluate, integrate 4 minus 3Z divided by Z minus 1, Z minus 2, dz, where C is a circle such that C is a circle such that absolute value of Z equals to 3 over 2. So this is the part. Absolute value of Z equals to 3 over 2. C is a circle. Let's say C is a circle. C is a circle. So Z, we start from here. What is the meaning of absolute value of Z equals to 3 over 2? It means that our contour is a circle. Centered at where? Centered at 0. So if it's centered at 0, this part will be the center. Radius what? Radius 3 over 2, that's 1.5. So 1.5, let's say this is 1.5, 3 over 2. And the other end, we are going to have minus 1.5, minus 3 over 2. So my contour will pass through 3 over 2 and minus 3 over 2 in this direction. So after that, what then shall we do again? Everything that is there is our f of z. Then we take the what? We find the pole. The pole is where the function stop being analytic. Equate this one to 0. The pole will be at where z minus 1, z minus 2 are equals to 0. If these three people are equals to 0 now, Mr. A is equals to 0, Mr. B is equals to 1, Mr. C is equals to 2. So z equals to 0, z equals to 1, z equals to 2. They are the pole. Then go back to contour. Z equals to 0 is here. That's 0. Z equals to 1. You know 1 will be around here. Let's say this is z equals to 1. Z equals to 2. 2 is greater than 3 over 2. That will be outside. It means that it's only this pole z equals 0 and z equals to 1 that are within the contour. Then we only find the residue at z equals to 0 and z equals to 1. So residue of 0 of this function, residue of 0 will be what? Limit. It will be limit as z approaches 0. No. Okay. Z minus 0 times 4 minus 3z divided by z minus 1, z minus 2. So z minus 0 cancel z. Then the other one now, put 0. So that's a residue of 0. If you put 0 here, that's 4, because this one will vanish. Put 0 here, put 0 here. This one will be minus 1 times minus 2. That's 2. 4 over 2, 2. Then the residue of the other pole, residue of 1. So residue of 1 will also be limit as z approaches 1 times z minus 1 f of z, 4 minus 3z divided